In this video, we want to look at sigma notation. Now, sigma notation is something that you have seen before in pre-calc, so we want to kind of review some of that and then add a new twist to it using some of our calculus. So sigma notation is this capital sigma, which means it's another word for summation or sum. Everything we're going to look at here is usually going to go from k equals 1 to n. So we start at 1, n tells us the number of terms, and a sub k is our formula. Now, we will look at a few examples here where we don't have k equals 1. When we get into the bulk of this, we'll always start at 1. So if we want to expand this, you remember we can expand this by starting at the bottom number, plugging 1 in for k. So this would be 2 times 1. Plus, and then we just count up. We put a 2 in for k, we put a 3 in for k, and we put a 4 in for k. So if we expand this sigma notation, this would be 2 plus 4 plus 6 plus 8. That is expanded form. Now, if we wanted to evaluate this and sum this up, we can add that up and get 20. So another example. In this case, we have j, and we'll have j starts at 3, goes to 6. So if we put this in, we have negative 1 to the third times 3 squared. Plus negative 1 to the fourth times 4 squared, plus negative 1 to the fifth times 5 squared, and then finally negative 1 to the sixth times 6 squared. Now, this notion of this negative 1 to odd and even powers, this is how you do a summation where it changes a sign from positive to negative. Because negative 1 to an odd number gives me a negative 9. Negative 1 to an even power is plus 16, and then minus 25, and plus 36. So this negative 1 is the mathematical way of having our terms bounce back and forth. Now, one of the things we're going to deal with as we try to expand these is having something like 1 over n in our sigma notation. Now you'll notice our k goes from 1 to n. So this n just represents some number. So for example, let's say I had sigma from 1 to 4 of 1/4 times 2k. If I wrote out my terms, this would be 1/4 times 2 plus 1/4 times 4 plus 1/4 times 6, and so forth. Now, one of the things you'll notice is every single term has 1/4 in it. So I could factor out the 1/4 and just have 2 plus 4 plus 6. The last one would be plus 8. But another way to think about it is this 1/4 does not depend on k. So I could take this 1/4 and move it out front and think of this sigma as 1/4 k equals 1 to 4 of 2k. We can do the same thing when we have the n. We could take that n and we can move it in front of the sigma notation because our k does not depend on that sigma. Now, we want to look at some rules of sigma notation. The first rule says if you have a constant in your sigma notation, you can move that out in front of the sigma notation. And that's basically what we did here by taking this 1/4 out in front. Our second sigma notation rule says if you have a plus or minus, you can split this into 2 sigma notations. So let's look at an example here. What we could do here, this should be an n, excuse me. What we could do here is I can pull this out in front, and I can split this into two. Now, 2 is a constant, so I can pull that out in front, and just k, and minus 1. Now, at this point, you're thinking, why would we want to do that? But just stay tuned. So those are our rules of sigma notation. Okay, so what that would allow us to do here is we could rewrite this as 3, 1 to 10 of k squared. And here we could split this up multiple times. We could make this sigma of k equals 2 to 8 of k plus 3 k equals 2 to 8 of k cubed. Okay. Now, I understand we could solve these by just plugging them into a calculator. We could multiply them out, expand them out, and simplify it. But what we want to look at here is we want to look at some formulas that allow us, when we have k or we have k cubed or when we have k squared, to use some formulas to evaluate those. So here are our summation formulas. Now, let's just kind of go through these one at a time. First, if we have the sigma notation of a constant, that becomes just c times n. So, for example, if we have sigma notation of 3 to the, and from k equals 1 to 10, that becomes just 3 times 10, which equals 30. Our other formulas. If we have the sigma notation of just k, we can write that as n times n plus 1 over 2, or n squared plus n over 2. And really, as we look at these formulas here, the form we are going to use is this far right-hand form. This middle form is very useful if you're going to be actually doing arithmetic and calculating, because it doesn't have anything you have to raise to a power. However, for us, it'll actually be more usable to use the formula all the way on the right. So for the next two also, you may just want to write down the formula to the far right. So if we have sigma of k equals 1 to n of k squared, we have 2n cubed plus 3n squared plus n over 6. And our final formula is if we have sigma of k equals 1 to n of k cubed, that is n to the 4th plus 2n cubed plus n squared all over 4. So as we can use these formulas, let's look at an example of k equals 1 to 10 of 3k squared. So first, with our constant multiple rule, I can pull the 3 out in front. And I get the sigma of k squared. Now, from our formulas we just looked at, our formula for k squared is 2n cubed, which in this case, my 10 is my n, 2n cubed plus 3n squared plus n all over 6. So that, if I go back, that is my formula for k cubed, k squared, excuse me. And then that is something then I could plug into a calculator if I wanted to actually get what the exact value is. Okay. So what we want to do is we want to combine this idea of taking something like this, splitting it up into multiple sigma notations, pulling out the constants, using those formulas, and we want to combine that with our idea of the limits as n goes to infinity. Okay, so let's look at this one. Find the limit as n goes to infinity of the sigma of k equals 1 to the n of k over n squared. Now at this point, we are just learning how to evaluate this. As we go into the next chapter, we will deal with where this limit comes from and setting this up and getting our information. But for now, we're just solving a limit that's given to us. So the limit doesn't change. Limit as n goes to infinity. This n squared is not part of the sigma. So that can be pulled out in front, and we can get 1 over n squared, and then we're left with sigma k equals 1 to n of k. So once we have the n pulled out of the sigma, and we have 1 over n squared, we then can write the sigma as our formula. So if we go back to our formulas, k is n squared plus n over 2. So this would be n squared plus n over 2. If I write this as, simplify those two fractions, this gives me n squared plus n over 2n squared. Now, if you remember when we looked before break at limits as n goes to infinity, we really only looked at our leading coefficients, because we said as n gets really, really big, this plus n doesn't really matter, and we just look at these leading coefficients, and so we get an answer of 1/2. Let's look at another one. It's maybe a little bit more complicated. We're going to do the same process, though. Once again, all of this will mean something as we go forward, and we'll have to set it up, but we want to get to the point where we understand how to do the limit first before we get into dealing with setting it up. So first, the 4 over n can be pulled out in front. Then our sigma can be split. So if I split this into 2, I have my first sigma is k squared over n squared plus sigma k sub 1 over n of 2. Now I'm going to do a couple things. I'm going to distribute this 4 over n back to both terms. So if I do that, I have the sigma of k equals 1 over n of 4k squared over n cubed plus sigma k equals 1 to n of 8 over n. And then my next step is to remove the n from each of these, and actually the number. So what that's going to mean is for the first one, I'm going to pull out the 4 over n cubed, and that just gives me sigma k equals 1 to n of k squared. And then in the next one, I'm going to pull out 8 over n, and that gives me k equals 1 to n of just 1. So what I'm trying to do is I'm simplifying these down to where I can get it to our formulas that we have earlier. So I can just plug it into one of my formulas. So that's going to give me 4 over n cubed. Now I have n k squared, which k squared is 2n squared cubed plus 3n squared plus n over 6 plus 8 over n. 1 to the n is just n. So this is going to give me the limit as I go to infinity of 8n cubed plus 12n squared plus 4n all over 6n cubed plus 8n over n. Now, as we evaluate these limits again, really remember as n's going to infinity, this doesn't matter. We just look at the leading coefficients. So this just gives us 8 over 6 plus 8. And 8, if I got common denominators, would be 48 over 6. So our answer is 56 over 6. So as we look at sigma notation, there's a couple things. One, and the big thing we're really going to be using going forward is using this limits with the sigma notation with our formulas. That's something we're going to have to continue into the next chapter. We just want to kind of introduce it here so we can understand the arithmetic and the math of how to evaluate this before we get into how we set these limits up. And then we'll also have a few on the homework, just some practice evaluating them, even doing some evaluation with those rules, just because we want to understand how those rules are used for going forward.